we have seen that complex numbers can be written in what's called algebraic form as a plus bi, where I is the imaginary number, the root of -1. We've also seen that there's a geometric interpretation of complex numbers as points on the complex plane, on two-dimensional plane. And there's one more way of describing complex numbers, which turns out to be very useful, in particular when we want to do things involving multiplication and division, and raising to powers and taking roots. And that's the polar form, which we're going to describe now. So suppose we have a complex number. So here's the complex number sitting here somewhere in the plane. Let's call the number z, and we know that it's of the form a plus bi, and this is a. A is its real part, and here is b, which is its imaginary part. Z can also be thought of or described in a unique way as this arrow, or what we called vector. It's just a different way of thinking of this point here in the plane. But what's important is that when we draw this vector can be presented in terms of what we call r, where r is the length of the vector, and what we call theta, where theta is just the Greek letter t, lowercase here. Theta is just the angle when measured from the positive x-axis counterclockwise. That's the angle theta. And if you know theta and you know r, you know precisely this point. Okay? It fixes that point in a unique way. So maybe let's write this. R, which is just the modulus, or the length of z, and theta determine z. Determine what the number is. So another way of describing complex numbers, this is called polar form, or sometimes called trigonometric form, and we'll see that it's related to trigonometric functions in trigonometry, is the following. We write z as r cis theta. And I have to explain this. Okay, so this is called polar form. Polar form of z. We write z equals r cis theta. And this I want to explain, why we write it like this. So how do r and theta relate to a and b? So if you think for a moment, and you know a bit of trig, of course, then this is a right triangle. So, and we know that in this triangle, this edge is precisely of length b, and this edge is precisely of length a. Therefore, suppose, so if we know, let's say, given a and b, how do we find r and theta? R is the hypotenuse of this triangle. We use the Pythagorean theorem. So r equals the root of a squared plus b squared. So if you know a and b, you can easily find r, right? What about theta? So the tangents of theta is the opposite edge divided by the adjacent edge. So tangent of theta is b over a, or in other words, theta is the arctan, the inverse function of tan, of the ratio b over a. So this is how we find r and theta given a and b. On the other hand, suppose we know, if we're given r and theta, if somebody describes this number in terms of r and theta, how do we find a and b? So the cosine of theta is A divided by R, right? So cosine of theta is A divided by R, and this implies that A is R times cosine of theta. A equals R cosine of theta. And the sine of theta is opposite over hypotenuse, is B over R. Sine of theta equals B over R, which implies that B cross multiplying or multiplying both sides by R equals R sine of theta. So maybe let's write it like this. So both of these facts imply that given R and theta, we can easily find A and B via these formulas. And now think for a minute. If we know A and B, then we know Z is written as A plus BI. But if we replace, let's write it over here. If we replace, let's write it up here. If Z is A plus BI, this in turn equals, I don't want to pass to the other board because I have all the information I need here, so I'll just write one more line up there. If Z is A plus BI, A is R cosine of theta, so I'm going to write R cosine of theta, plus B is R sine of theta, R sine of theta times I. And often we write the I over here. R cosine of theta plus R plus I R sine of theta. This is exactly equal according to this relation between R theta and A and B. And therefore, we can pull this R out, and we have R cosine theta plus I sine theta. And this is the polar form of a complex number, and it's abbreviated because it's kind of long, and one gets lazy to write it like that. It's abbreviated just by, let me color them in blue, taking the C from cosine, the I from the imaginary I, and the S from sine, and it's abbreviated as R CIS, often pronounced cis, RCIS of theta. That's this way of writing. Okay, so this is how you pass from one way of writing to the other. Whenever you see this, it's just an abbreviation. You should automatically, either in your head or on when you actually write in order to do calculations, this is just shorthand for writing this. This is what you really mean. Okay, so you can think of this as a new function of theta, but it really is just an abbreviation for this expression. Okay, so this is polar form or trigonometric form of complex numbers. By the way, I should remark that I drew here everything in the first quadrant, okay, where A and B are positive. It's not hard to see that if you take numbers in other quadrants, which correspond to bigger and bigger thetas, you would get the same relation. There's something a bit delicate about this theta determined via the arctan, and I'll mention it in a few minutes. Okay, so just some terminology that we should add. R is called, does anybody have a guess? Very good. R is called the modulus because that's what it equals. Okay, so R is called the modulus of Z. And theta, sometimes called the angle, that's also okay and clear what you mean, but its more formal professional name is the argument of Z. So R is the modulus and theta is the argument. Okay, that's just terminology. Remember that A and B also had names. They were the real part and the imaginary part. Okay, so let's do a couple of examples. So suppose we have the number z equals 3 cis, or cis, of 270 degrees. By the way, you can either work in degrees or you can work in radians. Better, much better, to get used to working in radians, okay? I know it's hard if you're already very used to degrees, but it really would pay off. It's a good idea to take time and go through the effort of getting used to radians. It will pay off, believe me. Okay, so here's still written in terms of degrees. Let's convert this number, which is given in polar form. Let's convert it to its regular algebraic form. So A is, remember that this is, let me write it because we're not accustomed to it yet. So this is just another way of writing 3 cosine theta plus I, sorry, not theta, 3 cosine of 270 plus I sine of 270. Right? This is just an abbreviation for that thing. So what is A? A is 3 cosine of 270. What is 270 degrees in radians, by the way? No? Yes. It's the entire circle is 2 pi. 270 is going 3/4 of the way, so it's 3/4 of 2 pi, or 3 pi over 2. Okay. So this equals, so what is the cosine down there at 3 pi over 2? By the way, if you have a gap in trigonometry, if you don't remember your trig very well, it is going to be important. It's going to be important here, and it's going to be extremely important in your calculus classes. So please take the time, if needed, to review trig. It's very, very important. Okay, so what is cosine of 270? Remember that cosine is the x component of the angle, so it's 0. So this is just 0. B is, the imaginary part, is 3 times sine of 270. Sine of 270. Sine of 270. Right, minus 1. So we get minus 3. So so z equals, in algebraic writing, 0 minus 3i, or just minus 3i. Okay, so here's a number given in polar form, transformed to algebraic form. Geometrically, it should also be rather clear, right? If this is in polar form, it means it's sitting on a circle of radius 3, right? That's its modulus. So it's sitting on a circle of radius 3, and exactly where on that circle? The angle is 270. So 270 rotates it all the way down here on a circle of radius 3. So we're looking at the number sitting here, where this is minus 3 on the imaginary axis. So this is precisely the number minus 3i. Clear? Good, everybody? Okay, let's do another example. So this will be example 1. Let's do an example of going the other way. So suppose we have the number z equals 1 plus root 3i. So here's a number given in good old algebraic form. Let's figure out what it is in trigonometric or polar form. So r is the modulus. So it's the root of the squares of a and b. 1 squared plus root 3 squared. Right? I hope you've had the opportunity to practice a bit and get used to this. So it's 1 plus 3, which is 4, root, r is just 2. And what is theta? Theta is arctan of b over a. So root 3 divided by 1. So it's the arctan of root 3, and the arctan of root 3 is pi over 3, or 60 degrees. Okay, because this is the angle whose tangent is precisely root 3. Okay, so it follows that, it implies that z itself is the number in polar form r to cosine of 60 plus I sine of 60. So CIS 60. Okay, or pi over 3, whatever you prefer to write. Okay, so this is how we go back and forth between the algebraic representation and the polar form. Okay, several remarks that I would like to make. Some of them are more delicate than others, but I'm really just going to mention them briefly. So some remarks. So the first remark, let's call it 1. Let's call it little I, like complex numbers. So the first remark is that 0 does not have an argument. It's not defined. What is the 0, the complex 0, the origin in the complex plane does not have an argument. The angle is not defined because it's just sitting there in the middle. So even in polar form, we just write z equals 0. That's 0 both in polar form and algebraic form, and it's well defined as a complex number. It does not have an argument in polar form, in trigonometric form. So that's one remark. Another remark is theta equals 45 degrees, and let's say theta equals 405 degrees. How did I get from here to here? I didn't just plug in a 0 in the middle. Right, I added 360. Okay, I added one complete circle, one complete rotation. Do you agree that these two numbers give precisely the same complex number in polar form? Okay, so theta equals 45 and theta equals 405 degrees give the same complex number. So we want to identify them. We don't want to think of, let's say, 3 cis 45 and 3 cis 405 as two different numbers. They're the same number. So therefore, the argument is not unique. Given a number, you can call this its argument, or you can call this its argument, and both will be correct. So the way around this, there are actually two approaches. One is to define the argument not as a single angle, but as a set of all possible angles that in fact prescribe the same location on the plane. Okay, so we define the argument as a set, as a collection of angles, namely the set. You already know this notation for a set. The set theta plus 360 degrees times k, where k can be any integer. K belongs to z. So if theta, let's say, is 45 and k is 1, then theta plus 360 times 1 is 405. It's the same, it belongs to the same argument, to the same set. And if k is minus 1, then theta minus 360, namely minus 315, is also the same number, would give you the same number. So theta, we think of the argument as a set of theta and all its multiple, plus all its multiples of 2 pi, either way, plus or minus, because k is allowed to be an integer. Okay, clear? Another way it could be done is to think, is whenever you see a number, always take the representative of this set, which lies between 0 and 2 pi, or 0 and 360. That's also done in some resources. I'm mentioning it, but I'm going to usually think like this. Okay. One more remark. So I would need let's do an example. So remark number 3. Be careful when finding theta. Okay, so what do I mean by careful when finding theta? I want to take you a couple boards back over to here. Remember that when we have a and b, we find theta using this function arctan, right? Because tangents of theta is b over a, so theta is arctan of b over a. That works perfectly well, and there's nothing to be careful about when you're indeed in the first quadrant. Okay, and that's in fact the example that we did using this. But when you move to other quadrants, to let's say a number in the third quadrant, and we'll do an example in a second, things get a bit delicate. And let me explain what I mean using an example. So suppose we have the number, let's say z equals -1 minus root 3i. So here's algebraic form for a complex number, and I want to convert it to polar form. So finding the r is easy, right? So r is easy. It's just the root of -1 squared plus root 3 squared. So this is 1, this is 3. 1 plus 3 is 4, root is 2. So the modulus is easy. But what about theta? So arctan, if I would just proceed according to the formula that we wrote there, arctan of b over a in our case is arctan of minus root 3, that's b, divided by -1. And this is just, the minuses cancel out, so it's just arctan of root 3. And arctan of root 3, if you go to your calculator and plug in root 3 and then press tan inverse, 10 to the -1, which is another name for arctan, what you would get, a calculator would give 60 degrees. But this is obviously wrong. Think of where this number lies. It has a negative real part and a negative imaginary part. This number lies somewhere here in the third quadrant, right? It has a negative real part and a negative imaginary part. Do you agree? So the angle corresponding to this number cannot possibly be 60. 60 would give you an angle here in the first quadrant. Okay? So what went wrong here is that the function tangent, its domain, where it's defined in a one-to-one way, and where we invert it in order to obtain the function arctan, is only for angles between minus pi over 2 or minus 90 degrees to plus 90 degrees. Okay? And if you take angles here, so this is an angle in the third quadrant. I didn't draw it precisely, just the idea. In fact, you're using the function arctan is not accurate. Okay, it's not defined there. So what we really need to do, is we're going to use the function arctan. We're always going to get an answer, between pi over 2 and negative pi over 2. So we're always going to get an answer here. And then we have to take into account the quadrant in which the number lives and find the angle in that quadrant which would be equivalent to which would have the same tangents as the angle that we got from the calculator using the function arctan. Okay, so what does it mean that has the same tangent? Remember, the tangent is the sine divided by the cosine. If both are positive, like here, or both are negative, like here, the tangent would be the same. Okay, so for 60 degrees, the corresponding angle here would be 240 degrees, would be to take the full pi and add another 60, or the full 180 and add 60. So the correct value of theta is 240 degrees. Okay? And there's no way around it. You calculate, you're going to get the 60, and then you have to look back at the number, think in which quadrant is it. If it's in quadrant 1 or 4, you're good. If it's in quadrant 2 or 3, you're going to have to take the corresponding angle in that quadrant. Okay? Play around with this a bit. I don't want to spend more time on doing 3 more examples. You can try them on your own, but it is a delicate point. You have to remember this, otherwise you get wrong answers. Okay, so this number, by the way, is what? Where was the number? Oh, there it is. So this number is 2 CIS of 240. So let's write it here. Z equals 2 cosine of 240 plus I sine of 240. So those were just a few comments that I wanted to make. Okay, what we want to discuss next is the multiplication and division in polar form. It turns out that when you want to add or subtract, don't do it in polar form. It doesn't make sense. You can try, and you'll see that there's no relation between the thetas of a sum to the thetas of the original numbers you added. Okay? And what you really want to do is add and subtract in algebraic form. It's very easy, right? We know how to do it. But multiplication turns out to be much easier and much more user-friendly, as is division, in polar form, and we'll discuss it in the next clip.